I want to thank Jeremy and Peter for inviting me to speak in this seminar. I have to say I'm here under somewhat false pretenses. I don't think of myself as doing tensor computations, but I think the connection will become clear early on in the talk, how it's relevant to this seminar. Anyway, my interests are in programming modern supercomputers. And these machines, which are warehouse scale machines now, are characterized by a couple of different things that make them different from previous generations of the machines. One is heterogeneity. So in particular, we have multiple different kinds of processors in these machines. These days, every one of these machines is built with accelerators, namely GPUs currently, but in the future, probably other kinds of accelerators, which gives you many different kinds. It gives you very heterogeneous performance. So there's different processor kinds, and they have very different performance characteristics. And then the other thing, which is become much more complex in the last decade, is the memory architecture. So it's not just a single node with a flat memory. Now there's a whole memory hierarchy within the node, in addition to the memory hierarchy that comes from the distributed aspect of these machines. Okay, so the memories are very non-uniform in their size and speed. And here's a picture of some of these machines, or the American machine at the top, the Summit, then one of the Chinese machines in the middle, and at the bottom is a Google or AWS, I can't remember which one, data center. And except for the blinking lights and nice panels, these are very, very similar architectures these days. The companies don't pay for the extra cabinetry. But otherwise, these machines are kind of converging on very similar characteristics. All right, so the question is then, how should we program these machines? So, if you want to think of them as a single machine and not have to program each of the individual technologies that go into them, how would we do that? And for the kind of work that we've been doing, the principle that we've followed is that really it's the data that matters the most, and not the compute. And so in particular, the data movement and how the data is placed in the machine is a first order programming concern in a way that it hasn't necessarily been in the past. And that this is the thing that really determines how well your programs run. Okay, and so the kinds of programming systems we've been looking at, and particularly Legion, is what we would call a data-centric programming system. And so the highlights of the Legion programming model, and these are the things I'll talk about the rest of the presentation, is how we handle data partitioning, okay, for distributed computation, the actual programming mechanism for that. All right, so what some of the partitioning primitives look like, something called mapping, and I'll talk about the mapping interface, and then a fairly recent addition to the programming model called control replication, which turns out to be quite important. So let's start with partitioning. So partitioning data is necessary for parallelism. If you want to get parallel execution, you have to divide your data up into chunks so that different threads of computation can work on them in parallel. And the question is, how should the data be partitioned? And so as an example, let's take in a regular graph, and we're going to do some kind of computation on this graph. Let's not worry too much about what it is. This happens to be an electric circuit simulation where the nodes are wires, and I'm sorry, the nodes are points where wires join, and the edges are the wires themselves. But the actual physics behind it is not so important for understanding what the issues are. So what we'd like to do is take this graph and break it up into pieces so that we can work on it in parallel. And so let's just say that we're going to chop it into 3 pieces. And for some reason, we've picked these 3 subgraphs as the ones that we want to distribute to, say, 3 different compute nodes. Okay, so how would we do that? Well, in these kinds of computations, typically the way you want to carry out these things is that you'll have a set of nodes. Okay, so this is a set of all the nodes, and then you're going to divide them up into what we would call the private and the shared nodes. So if you look at each of the pieces here, the nodes in blue are contained entirely within the piece, meaning they're not connected by an edge to any other piece. And so these are nodes that we can compute on without ever needing to do communication to other parts of the graph. Okay, these nodes are only connected within the individual pieces themselves. And then the red nodes, the shared nodes, are the ones that are on the border of the pieces. So every red node here is connected by at least one edge to a node in another piece. And so these are the ones where communication is going to have to happen. So these will have to have their state communicated, and we might want to put them in a different place, for example, where that communication will be cheaper, whereas the blue nodes can potentially be buried very deeply inside the memory hierarchy, because we're not going to have to move information from them very far during the computation. Okay, so we like initially, at least for algorithmic reasons, to kind of recognize the difference between these blue and red nodes. And so we're going to partition our nodes into those two sets. And then we're going to take both the private and the shared nodes, and we're going to further subdivide them into the individual subsets for each of these pieces. So for example, for piece one here in the upper left-hand corner, we'll have a set of the private nodes, and we'll also have P1, which is the set of private nodes for piece one, and then red nodes S1, the shared nodes for S1. But then we're going to have one more set, okay, which is the ghost nodes. And these are the shared nodes that are in other pieces connected to piece one. So those are these particular green nodes. So for piece one, these are the three relevant subsets. We have the private nodes, we have the shared nodes inside of piece one on the boundary of piece one, and then we have the green nodes that are on the boundary of another piece and connected to piece one. So these are shared nodes, the green nodes, of other pieces that are connected to the shared nodes of piece one. All right, and these are the three relevant subsets for piece one. They're similarly, we would have the same three sets for piece two and piece three. And we wind up with this structure here in the upper left-hand corner, okay, which we call a region tree, and reflects the hierarchical subdivision of the nodes into these subsets. Okay, so we have first we divide the nodes into the private and shared, and then to divide the shared into the actual, what we call the shared nodes for each piece, and the ghost nodes in other pieces. All right, and then this is encoded in Legion in a programming model that looks like this. All right, so we have tasks, which are the unit of parallel execution. These tasks take these sets, which we call regions. Okay, and regions are in general n-dimensional tables, so they're actually tensors, and they have typed columns. So each element of the tensor can essentially be an object or a set of fields that carry the information associated with that point in the n-dimensional space. All right, and then there's information that's also included in the signature of these tasks that say how the task is going to use these tensors. So in particular, we need to know things like whether the task is going to read or write the particular region, and which fields it is going to read or write, or whether it's going to perform reductions, associative commutative reductions to some elements of the tensor. Okay. And so these privileges declare how a task will use its arguments. All right, and then the body of the tensor looks like a normal computation, and that's not something that that we'll focus on in this particular talk. Okay, So, all right. And one thing that's worth pointing out is, this particular task, notice that it uses the shared nodes and also the ghost nodes, and it uses the same field in a reduction. So recall that the shared nodes and the ghost nodes here are two different partitions of the same data. So these are actually two views, two ways of taking the shared nodes and viewing them, okay? Different organizations of the same data. And this is very, very common in Legion programs, that we'll have multiple views onto the data, so multiple ways of partitioning the same tensor. And then we'll have tasks that either use one or the other, or potentially both of those views at the same time. All right, so, that is, in a nutshell, the model for Legion. This one slide here, I think, kind of captures the flavor of the programming model. I'll just say a couple of other things, since I realize most people won't have seen anything like this before. The reason for distinguishing tasks as units of computation is that the idea behind a task and the way tasks are designed, they can be run anywhere in the machine. So a task can be assigned to any processor anywhere. They're self-contained units of computation. All right, and Legion will organize the data movement. If two tasks if one task produces some results, another task requires those as input, then Legion will arrange for the movement of the data from wherever the first task runs to wherever the second task runs. So there's a lot. So the runtime system has a lot of knowledge of how tasks are related to each other. That comes from these privileges, and will orchestrate all the data movement without the programmer needing to be involved. The fact that you have these complex, potentially partitionings of the data, this is what implies communication. So if one task uses, say, a set of shared nodes, and another task uses a set of ghost nodes, those may overlap, and the system will need to figure out what data needs to be communicated. Okay, and so where you see multiple views onto the data, that's where you can have potential aliasing of data and potentially very complex communication patterns. I will say one more thing before going on, and that's just that this expressive partitioning of the input tensors is the unique feature of Legion. Probably the thing that makes it the most different from other systems that try to that provide programming models for these large-scale distributed systems. And in particular, the ability to have multiple views onto the same data is a feature I don't think any other system has pursued. All right, so what are some consequences of some of the lessons that we've learned from having a few years of experience now with writing programs in this style? So the lesson one is that this is a good way, and perhaps a necessary way to achieve compositionality of software. So what we found is that having multiple partitions of the same data is really needed for scalable software composition. And the simple kind of first principles argument for this is just to think about what if you were to write a program that was going to use a couple of different libraries that had been written independently and that use the same data. So say you have some operation that two libraries that work on matrices. There's no reason to assume that since these were written independently that they use the same data partitioning. The data partitioning will be a function of whatever's best for the algorithm. There's no reason to believe that they would want to chop the data up the same way. So if you want to use both libraries in your program, you will inevitably come to a situation where you have multiple views onto the same data. And if your programming system can't deal with that in some nice way, then you're going to wind up either having difficulty expressing your program, or with a lot of extra data movement to kind of undo one partitioning and then redo it in the other style. All right, so So just composition and the fact that you want to be able to have independently written pieces of software that you can put together kind of drives you to this conclusion that you're going to have multiple partitions, different kinds of partitions of the same data in your program. All right. So as a result, one of the things that's happened in Legion is that we've evolved an entire partitioning sublanguage. So Legion has a very rich subsystem of partitioning primitives. And this is, while every parallel distributed programming system has data partitioning of one form or another, this is particularly well developed in Legion. And there's a lot of ways of partitioning things that you don't see in other systems. Each of these primitives is designed to be efficiently implementable in a scalable parallel way. Okay, so these are built-ins, but then they compose. And so the idea is that you have a set of primitive partitioning operators and then ways of putting them together to build complex partitioning strategies. So let me just say what a few of these are. Okay. So, I just say, the easiest one that every system has is just take a tensor and chop it up into equal pieces and don't worry about, what those, exactly what those pieces are. Just let the system automatically somehow divide the system into equal amounts. Okay. So Legion has that. Now, a slightly more, sophisticated operator that is used pretty commonly is what we call partitioning by field. So let's say we have a tensor, okay, and it has some properties. In this case, it's the nodes of this graph, and it has some properties like voltage. But then it's also going to have a bit mask field saying whether the node is shared or private. Okay, and so some other computation that we write, which could also be a parallel computation, will fill in this field. All right, so this is potentially a computed field, and so the partitioning here can be data dependent. And then what partitioning by field does is just say I want to partition the data based on some field. So the field has some finite set of possibilities, and we'll have a number of subtensors equal to that number of possibilities with each. In this case, each node that's labeled shared going into the shared tensor, and each node that's labeled private going into the private tensor. Okay, so this is the data-dependent partitioning just by filling in a field of a tensor and then doing the obvious thing to partition it. Okay, and you just have a primitive operation in Legion that takes a region or a tensor and a field and does the obvious thing. All right. So partitioning by field and equal partitions are examples of what we call independent partitioning operators. So this is a partitioning operator that doesn't depend on any other partitions. All right. The composition operators in Legion are what we call dependent partitioning primitives. And these are ways of computing new partitions from existing partitions. And so this is useful when you have multiple tensors that you want to co-partition in some way. Okay, and there are essentially 5 of these. There's set theoretic dependent partitioning operators based on union intersection and the difference of partitions. And I'll give examples in a second so it becomes clear how this works. And then something using what we call image and pre-image computations. Okay, so I'm going to explain those first, and then we'll look at the set operations. So let's say that we have a existing partition of a tensor or region. All right, so here I have some region, and I have colored it, by its partitioning. So everything that's in blue is in one subtensor, everything that's in red is in another subtensor, everything that's in green is in a third subtensor. Okay, and this set of dots here in the right column is a pointer field that points into another region. All right, so there's some relationship between these two tensors. Okay. And what we want to do in this, what partition by image does is construct a compatible partition of the pointed to region. So we treat the first tensor here as a function, okay, where the range is the second data set here, all right? And then we just propagate the color from one to the other. So in this case, I can think of these arrows, these pointers, as having the same color or subregion as the source, and then I just copy that color over. Okay, so for example, if something is in the red region in region 1, then it'll be in the corresponding red region in region 2, and things that both have the red color will, that were in the same subtensor in the first on the left hand side, will be in the same subtensor on the right hand side. All right, and there's one wrinkle here. Okay, since this is a function, there's nothing that stops it. There's nothing that requires it to have every element only be the target of a single of a single source element, right? So this element here that's in yellow is pointed to by both something from the green subregion and from the red subregion. And so what's the semantics of that? Well, it's just going to be in both. So there's nothing that says that that these partitionings have to be mathematical partitions. Again, we use the word partition, but in fact, things can, in general, these subsets can overlap. All right. So when we talk about dividing up a tensor into subsets, they really are just subsets, and the subsets don't have to be disjoint. Okay. So we'll use a somewhat oxymoronic term, disjoint partition, when they're truly disjoint, and we'll just call it a partition otherwise. And if we had a better name, we would probably change our terminology. So I apologize for the abuse there. Okay, so this is one method of constructing a partition of a tensor from an existing partition. There's a dual operation that does pre-images instead of images. So if I have an existing partition of a tensor, okay, and then I have another tensor that points into that, then I can just propagate this partitioning backwards to the source of that pointer. And in this case, there's no chance of, it's guaranteed that if the original partition was disjoint, then the pre-image will also be disjoint, okay? Since every pointer must have a unique source, all right? And so in this case, you can see the compatible partition here. All right. And these two operations, images and pre-images, are extremely useful for co-partitioning tensors when you have complex data structures that you've represented as multiple tensors with interrelationships. Okay, so this is actually quite common, and these particular operations really seem to be quite general in terms of being able to express what you would like to do.
I asked a question there, Alex.
Yeah, go ahead.
So you said that the partitions don't have to be a partition because they can overlap. Do they have to cover the region? Does everything?
They do not, actually. They do not. Yeah, it's not required that they be complete either. Right. Yeah, so then by far the most common case is what we would call a complete disjoint partition. Right. All right, but they neither have to be disjoint nor cover the set.
Right. Okay. Yeah. Great.
Thank you. Both of those actually do come up in practice. Right. Okay. Okay. So now let's come back to our example of a graph. So I've talked about the nodes, but in fact, what you would generally do is you'd also have a separate tensor for the edges. Okay, and the edges would have like source and destination pointers that point it back into the nodes relation. All right. Okay, so here's an example of a data structure that's represented as a couple of different tensors. And it makes sense that if you're going to partition your nodes a certain way, you would like to partition your edges in a compatible way so that the edges that are associated with certain nodes wind up in the same place as those nodes. That will be much more efficient than partitioning the edges in some random fashion with respect to the nodes. Okay, so I'll give you an example here. I'll actually work through a full example of using dependent partitioning to do some of this, to compute the ghost nodes. All right, so we won't do all the sets, but we'll just talk about how to compute the ghost node partitions. Okay, and so what's the idea? So the idea is that for each piece, we want to start with its set of shared nodes. Okay, then we're going to add to the set all the adjacent shared nodes, okay, that are in other pieces. All right, and then we'll subtract out these shared nodes that we started with. All right, and that will leave us with exactly the ghost nodes. Okay, so we'll always be talking about things that are in the shared set. We'll never look at the private nodes in this computation, but it'll follow this pattern. We'll start with the shared nodes. We'll add their neighbors that are also shared nodes, and then we'll subtract out the original set of shared nodes, and that will give us the ghost nodes for the piece. Okay, so the picture will look like this. We'll find all the adjacent shared nodes, everything reachable in one step, and we'll have this set, and then we'll subtract out that original set, and we'll wind up with the ghost nodes for that piece. All right. Okay, so how do we do this? So we start out by partitioning the nodes by field, okay, into the shared and private pieces. All right, and just note here that partitions are first-class objects in Legion. So what you get out of partition by field is essentially an array of tensors. You get an array of the subtensors, okay? And like piece one is the first, the first element, piece two is the second element, and so on. All right. Okay, and so then we can pull out the private nodes and we can pull out the shared nodes from that partition. Okay, so now we're going to focus on the shared nodes, as I said before. All right, so then for the private part, actually, I guess I didn't say it correctly. We're going to, I guess I'll show the partitioning here of the private part as well. All right, so for the private part, we're just going to have another field that says what piece each node should be in. Okay, so this will give us the subtensors for each of the private pieces, and we'll do the same thing for the shared pieces. Okay, so now we have all the private and shared nodes, all right, for each piece. Okay. All right, now we still have to compute the ghost nodes, okay, and this is the interesting part. Okay, so what are we going to do? Well, so the first thing we're going to do is we're going to partition the edges by their source node, okay, and here we're just going to look at the shared nodes, and we're going to find all the edges that are connected to a shared node. All right, as its source, okay, and that'll give us one partitioning of the edges. All right, and again, this is an array of tensors that's organized in the same way as the shared nodes. Okay, so all the shared nodes that have a certain source, all the shared edges, all the edges connected to a shared node that of a certain source will be in the same partition as that shared node. All right, and we'll do the same thing for the destination. We'll find all the, we'll organize all the edges by whatever. A separate partitioning of the edges that are organized by destination node. Okay, so now we have all the edges that are attached to a source node that's shared or a destination node that's shared. Okay, associated with each of the shared pieces. All right. Okay, and again, notice the thing here that we're passing in here in the middle is a partition, right? So we're getting another compatible partition of the edges. Now we just take the union of those two things. Okay, so now for each piece, we have all the edges that are attached to the shared nodes in that piece. Okay. All right, and so now we can take the image of those edges. We just take all the, we take all those edges and we look at all the sources attached to those edges and all the destinations attached to those edges. So for each shared node in a piece, we're looking at all the shared nodes that are attached, either as a source or a destination, to the nodes in that piece. Okay, and then finally, we take the union of those two sets and we subtract out the original shared partition, and the things that will be left are the shared nodes that were attached to, that were connected by an edge in that piece. All right. Okay, so I don't think the details here are super important. I hope that you were able to kind of follow that. It's easier if there's a picture. I apologize that I don't have an animated picture for this. But I think the high level story here is, first of all, here's a set of primitives. that I can actually write a little program by composing them to compute a fairly complex relationship, okay, using images, pre-images, and set operations. Second thing is that in order to do this, I had to have multiple partitions of the same data. Okay, I mean, I've partitioned the same sets here in multiple different ways. I have, like, not just two, but 10 different partitions. Now, in the end, I'm only going to use a handful of these. Many of these were just intermediate, steps that were convenient for getting to my destination. But the fact that I was allowed to partition the data multiple different ways is what made it possible to write this program. Okay, so this is very much the style of Legion programs. You see lots of code like this to slice and dice the data and set things up in exactly the right way for whatever algorithm, whatever distributed algorithm you're going to use. All right.
Alex, there's a question in the chat from Rishi Nikhil, which may be appropriate now. Can you relate Legion and the current state of the art to early work in high performance Fortran in the 90s, which also had partitioning notations?
Yes. So there is some history there, and so high performance Fortran, definitely was going down this path of allowing expressive partitioning. High performance Fortran, I think there's many differences one can point out, but I think one of the kind of key ones is that a high performance Fortran was really going for a statically oriented approach where a compiler understood all the partitioning without running the program. So this is all dynamic. This is all stuff that is actually computed at runtime, okay? And the analysis of it is all done at runtime, which is greatly, it's more expensive in the sense that you have the overhead of doing this as part of the running computation, but it also greatly simplifies and makes much easier for the system to know exactly what's going on. Okay.
Of course, the programmer has to intervene to say which partition it is that's wanted.
Yes, that's correct.
Yeah. All right, great. Thank you.
Yeah. Okay. So lesson 2. So I think the second lesson is that these partitioning primitives are really a very nice way of talking about how you divide up your data. It's much better than constructing partitions by hand. And by hand, I mean, writing lower level code as an MPI where you set up your own buffers and have code that the runtime system, that the language system doesn't understand, to pack data into those buffers. So this is more maintainable. It's much easier to change your strategy. It's more performant in that we're able to implement each of these primitives in a high performance way. Okay, so the composition tends to be reasonably performant, and it's also more scalable. We pay particular attention to the scalability of these primitives when we implement them. All right. Okay, so now let me talk a little bit more about the programming model, and we'll say say a little bit more about about how it works and how it takes advantage of these of the data partitioning and these partitioning primitives. So I mentioned before that this unstructured code is a circuit simulation. And it takes 2 tensors, one of nodes and one of wires, which are partitioned into in the way that I described before. Okay, and there's several tasks that constitute a single phase of the simulation, and it's a time step loop where these tasks are run over and over and over again. All right, and 2 of these are calculating the current and distributing the charge. Okay, and so you need to calculate the current for each piece. And here I've explicitly written that out rather than in a loop. And you have to distribute the charge, across each piece. All right. Okay. And then this notation here, these colored boxes are meant to indicate, okay, these tensors are being passed as arguments to these tasks. All right. Okay. So, and then you would write these other tasks, calculate currents and distribute charge. So notice that you can have subtasks. So just like you can recursively decompose data, you can recursively decompose computation as well. Okay, so tasks can call subtasks. So in the execution model here is that this is the programmer looks at this as a sequential program. You can think of it in a sequential way. So tasks are going to be issued in program order, and the system is going to guarantee that you'll get the semantics that you would have gotten in a sequential execution. All right, so tasks without any dependencies that don't depend on any other tasks can run in parallel. These dependencies are detected automatically by analyzing what region arguments are being passed and what the privileges are. And that's done at runtime. So, okay, now what we haven't said anything about is where any of this actually executes. So nothing in that program said that a particular task should run on a GPU or on a particular node or anything else. Okay, so the mapping interface then is a piece of the application that makes these decisions, and it's segregated into a separate API. So the idea is to separate this concern of how tasks and data are actually placed in the machine from the source code itself, so that it becomes easier to port these applications to new machines. Because by separating out the mapping, you can leave the source code alone, and when you move to a new machine, you can just focus on changing how it's mapped. All right. So to do mapping, the application has to select where tasks are run and where regions are placed. All right. And so if I have some machine architecture, say some mix of CPUs and GPUs, and then some memory hierarchy that is associated with those processors, I'm going to have some task graph. Okay, so you're going to wind up with some tasks that are launched, and they're going to have some dependencies between them. I haven't explained yet exactly how that works. We'll look at that a little bit more in a minute, but essentially there's going to be a partial order on the execution of tasks. All right, and they're going to have to be assigned to processors in the machine. So maybe some of these tasks will get mapped to CPUs, and some of them will get mapped to GPUs. And then we're going to have a bunch of tensors, organized in some tree hierarchical fashion like this. And the ones that are being used by these tasks will have to be mapped to memories that are consistent with the assignment to processors. So I have to map the region arguments to memories that are actually visible to those processors. So that's one constraint that the mapping interface will enforce. Okay, so this is a mapping. Tasks get assigned to processors, data collections get assigned to memories. And this is done through a separate API where applications can write their own policies. Okay, we provide some default policies, but this is all programmable, and those policies can be replaced with custom mapping strategies for a particular application. All right. Okay. So this decision to kind of separate out the mapping interface, I think, is another, one of the important ideas in Legion that has turned out to be extremely useful. And it's not just about portability, okay? It's also just about tuning for an individual machine. So one of the things I think that goes wrong for a lot of projects in writing these large-scale distributed programs is that you have to commit very early to your mapping. So you have to decide when you're writing the code, am I going to put this on the GPU? And if you're going to put it on a GPU, then you have to write a bunch of CUDA, and you have to write, whatever data movement operations are needed, say, to get the data there, and your code, becomes kind of locked into a decision that particular piece of the puzzle is going to be, committed to the GPU. And then when you go to run your program, if you discover that actually was a bad decision, like for whatever reason, that piece of the computation shouldn't be on the GPU, it should really be on the CPU, you have a significant rewrite in order to change your strategy. Okay, so you have to actually go and modify the program. Often you have to rewrite, you have to write some new code, for the task. You may have to change your data movement completely around, all kinds of things might be disturbed by having to undo that decision. In Legion, it really is just a one-line change to change that mapping. Okay, and I haven't, said exactly how we can get, code generation for both GPUs and CPUs, but we do support that. And so it really can be something where you can just flip a switch and change your mind about, where things run. And this allows experimentation with the mapping. And often one of the reasons Legion programs can perform better than, say, a comparable MPI program is not because the MPI program couldn't have been written the same way, but because we had the ability to iterate on the mapping and change our minds and try out lots of different strategies and find one that worked particularly well for the application. So it just, much more productive when it comes to tuning than having to rewrite large amounts of code. Okay. So this idea of late binding these decisions saves a lot of recoding and also allows you to make the decisions when you actually have the information rather than when you're starting the project and don't really know, exactly what's going to be important yet. Okay. All right. So so the last thing I wanted to talk about, and this is maybe less relevant to this seminar, so I will spend, I'll probably go through it more quickly, is who launches subtasks, okay? And there's a couple of different answers in systems today. One is that you just have a centralized controller. So actually your entire distributed computation is, the decision about how to map things, about where to run things, about launching all the tasks, that's handled in a centralized manner. And this clearly is a scalability bottleneck if you want to run on very large machines. So if you have one node that's trying to manage 10 nodes, that's not so bad. If you have one node that's trying to manage all the tasks on 1,000 nodes, this gets to be a performance bottleneck in and of itself. So it's very hard for a single node to keep 1,000 nodes busy. Okay. So so another strategy is to replicate the parent task, whatever is launching the subtasks, across multiple nodes, and have these replicated parent tasks cooperate to each do only 1/nth of the work. Okay, so essentially, if you're trying to launch 1,000 tasks, one way to do that is to have a parent task that launches 1,000 tasks. Another way to do that is to have 100 tasks that each launch 10 tasks. Okay, and they cooperate to only, just make sure they launch a different set of 10 tasks, and that all the communication still happens and everything. So you use the distributed resources to execute a single task in a distributed fashion. And this can obviously scale much better. Okay. And the important thing here is that when you split up a task and replicate it, you still have to implement single task semantics. So if you have 100 copies of the parent task running, they need to cooperate in a way that they, achieve the same result as a single task, but they just have many more resources for managing all the subtasks that parent task needs to launch. Okay. So this is, we call this control replication. So basically replicating the control part of the program. You can think of it as taking a kind of task-based system that has a single root and then fans out launches, and automatically converting it into an SPMD style program. Okay, that has the same semantics. And so this is a way of scaling, to thousands of nodes without having to change the programming model. And has proven to be crucial, to large scale computation for at least for the style of programming system that Legion provides. Okay, so the region-based data model, it's similar to data frames, relations, and databases. Tensors, obviously, it really is tensor-based. One of the innovations is that partitioning is a first-class citizen in Legion. So you have a very expressive partitioning system, and partitions are computed dynamically and allows arbitrary number of views or partitions of the data. Task parallelism is implicit in Legion. I didn't say that explicitly before, but tasks can have arbitrary subtasks. They declare their privileges on their region arguments, and then the system figures out what the dependencies are between them. And then tasks appear to execute in program order. Okay, so they execute in parallel when the data dependencies permit. All right, and then you get portability by separating mapping from the functionality, from the other concerns in the program. All right, I'll just say a few words. If there's a question, that would be a good time.
There are a couple of questions in the chat. One from Martin Berger. Legion's clearly about scalability in the large. Have you considered how this scales in the small? For example, distributing tasks between different processor cores efficiently. The trade-offs are very different in the small.
Yeah, so I mean, one thing we do want Legion to scale down. So we want it, to be useful and on a single node as well as on very large systems, because that's mostly where people develop. Okay, and the idea is that you can run it on your laptop and get your program working, and then move to larger machines. That doesn't completely answer your question. I think one way of kind of answering it in a quantitative way is what's the granularity of tasks that Legion can support efficiently. Okay, because it's a dynamic system, it imposes overheads, and if your tasks are too fine-grained, then the overhead of managing a task, could exceed the time that it takes to run the task. All right. So the experiences and the guidance we give people is that if you're writing programs with tasks that run in the millisecond range, you're going to be fine. Okay, so like as long as your tasks are a millisecond or a couple of milliseconds in length on average, doesn't have to be every single task, but the average length of a task is a millisecond or two, then your performance will be good. If you're an expert Legion programmer, you can get that down to 400 or 500 microseconds and still get good performance. You get down into the 100, 200 microsecond range, and that's too fine-grained for Legion to do a good job with. Okay.
Good, thank you. Yeah. Another question from Rishi and Nikhil about mapping. Can any compute node do any computation, or are there constraints about what each compute node can do? For example, specialized accelerators.
Yeah, so the way this is set up in Legion is, the responsibility is, again, put back on the application. So every task can have multiple variants. So a task doesn't have to have just one implementation. So for example, you might have a CPU implementation and a GPU implementation of a task. And if you only have a GPU implementation of a task, then that task has to run on a GPU. And so that becomes a constraint of the mapping. All right. There are other kinds of mapping constraints or variants that you can have. So for example, you could have tasks that were optimized for certain data layouts, for structive arrays versus array of structs. So there's some applications have many different variants of tasks, but that's primarily the way that constraints on where things can run get into the system is, like what do you actually have implementations for? Okay,
good. One from James Demmel. Where in the Legion framework would one apply a graph partitioning or related algorithm to choose a partition?
Yeah, so typically, well, first of all, let me say it depends a little bit on the nature of the algorithm, but many of these, the partitioning is done up front. So like the first thing you do is load your data and partition it, and then you run your algorithm. Okay, and that's probably 90%. There are applications, I mean, like anything that requires dynamic partitioning is certainly possible. So things like AMR are expressible, where you would change the partitioning as you go along, because everything is dynamically computed.
Yeah. Martin Elsman asks what memory management scheme is used. Is that also region-based in some sense?
Well, this is why it's called regions, right? I mean, so there's a history in the programming languages community of region-based work, and Martin knows it very well. And that it definitely, the name was, honors that tradition, and it is a dynamic region-based system in the programming languages sense. Regions are reference counted, and there's a distributed reference counting garbage collection system that underlies. That's part of the implementation. And actually, I was going to say, just a little bit about that in a minute here. So maybe if there's another question, I could race through the last few slides.
There are a couple more questions.
Okay, let's take them.
Which is, yeah, nice. Brent Spilner asks, do you have real-world examples quantifying efficiency gains of Legion compared to hand-mapped computations?
Yeah, these are in the papers, and actually I can talk about that too. So right. Maybe I'll spend my time on that instead of the details of the runtime system. Yeah.
Peter Brahm asks, do support libraries exist to convey previous experience or ML optimized partitioning? And similarly, libraries with machine architectures that are common to support mapping?
I didn't understand the question.
I think trying to load, I mean, maybe Peter, you can elaborate.
One would think that partitioning decisions might be made by a third-party program that have done machine learning. Similarly, many computing architectures are rather common ultimately, and so the mapping could be supported perhaps by the experience or work of others.
Yeah, so it's possible to have kind of external constraints on the data. Say, you have to deal with the map. Here's the data. It is in this format. And then you have to deal with it, right? And so that can be imposed, as an external constraint on a program. And then, all the decisions and the runtime analysis will flow from that. Yeah. So
I think the example, your running example, you computed the shared and private attribute and then use that for partitioning, but you could just load that from a file or
correct
from some external service.
Right, but also you could be interacting with a running application that only provides you could use a non-Legion library that only provides the matrices, say in a certain sparse format, and then you can just say, okay, this is the format, and then the application has to adapt to that. So you would just say, this is the partitioning of the data. Okay, let me. I'm going to skip over the runtime stuff. If anybody has questions on this, I'd be happy to answer it. I'm going through many slides here in a hurry. Let me just say a few words about results since that came up. Okay, so S3D is a big combustion simulation. It has two parts. There's a nearest neighbor physics communication, which is data parallel, and then there's very complex chemistry that has a lot of task parallelism. Just the different reactions are dependent on each other, and it actually varies with the mechanism, which particular reaction you're simulating, what exactly the dependencies are. And it's characterized by very large working sets per task, so there's a lot of data and not much compute here. So this application is mostly limited by data movement. All right, and so here's some old results, kind of showing how this scaled, a few years ago on what was then a very big machine, and the Legion version was about 3 times faster than the MPI version at the time. But as you scaled out, it got even better. It got to be 7 times faster at large scales because it did a better job of overlapping compute and data movement. Okay. More recently, some work on fast graph analytics. The conventional wisdom here is that graph analytics can't really take advantage of distributed memory. But bottom line here is that with a careful mapping, we were able to show that you actually could have distributed memory, take advantage of multiple GPUs in particular attached to a node that would be better than large CPU systems for graph processing. Okay. Probably the most recent thing is a drop-in replacement for TensorFlow and PyTorch built on Legion that takes advantage of the ability to partition the data in multiple ways. So very briefly, TensorFlow and PyTorch basically only have one way of partitioning the data. There's a few things you can do, but they don't really have the expressive power to think about parallelizing deep learning in more than a couple of dimensions. Okay, and in Legion you can express many more strategies, and this turns out to actually make a difference. Okay, and so you can get significantly better performance, particularly for training, as well as for inference, with deep learning if you choose different partitioning strategies than the standard ones. Okay, and this has been pretty well demonstrated here. And probably the most dramatic example of this is a case study from Facebook that they did. So the training throughput of FlexFlow, which is this deep learning library built on top of Legion, compared to using TensorFlow, down here at the bottom with a couple of the standard strategies, and it's just this is really just about the partitioning strategy. Just chopping up the data in a different way leads to much better performance. And the other interesting point I will make here is that this one of the things FlexFlow does is it actually searches for this partitioning strategy. So given that this is a programmatic thing in Legion, you can actually try out multiple different partitioning strategies and kind of automate, finding the best one. All right, and so this particular strategy was chosen automatically and maximizes the the performance gain. Let me mention one more thing. Another project, which is not our project, but is at NVIDIA, is a drop-in replacement for NumPy based on Legion. And essentially, NumPy does a large array computations and has been accelerated on single GPUs previously. This is a distributed version of NumPy that does partitioning of those large arrays. So it automatically, figures out how to partition the tensors and spread them out. And so to accelerate very large NumPy programs over large distributed machines, this is a solution. And this has actually been rebranded by NVIDIA. It was an NVIDIA research project. Now it's an NVIDIA product called cuNumeric. And this was just announced at the most recent GTC. So this is something that is now, supported by NVIDIA. All right. And then here are some results. Kind of showing that running out to very large numbers of GPUs with some interesting NumPy computations. Okay, so I think I am out of time, and I've already said most of this. So let me just finish with a couple of thoughts. So I emphasize performance. But I just want to circle back and say that in the end, it's all about productivity. So I mean, you can always get performance with enough effort. So and you can do that in any programming model. You could do it in assembly language if you had enough time and enough people and enough money. So it's really about productivity. I mean, how hard is it to get to a certain level of performance? And the Legion philosophy here is to give you an expressive data model and a compositional system that kind of tries to separate concerns, especially with how things are mapped onto the machine. This does require more initial work from the programmer. You have to think a little bit about how you want to organize your tensors. You have to think about how you're going to partition them. Okay, but it makes the later stages easier and more flexible. So when you actually do have performance results and you actually are running on a machine, it's much easier to change your strategy at that point and experiment and find a good mapping and and even changing your partitioning strategy often isn't that difficult. And that's where we've generally found improvements, is that we're able to iterate much more quickly once we have a working program in this paradigm. And I'll stop there. I can stay on for another couple of minutes. I apologize for kind of rushing here at the end, but you've been a great audience. Thank you.
Great. Thank you very much, Alex. That's wonderful. So thank you. On Zoom, you can clap with your Zoom button. There is a question about the runtime system bit that you skipped over. Is there? Do you have links to the papers? For example, are there links to the papers or information about the papers in the slides? And are you willing to share the slides?
I'd be happy to share the slides. All the papers are linked from this website.
Right.
So this is all public stuff, and so and since we're essentially a runtime, we're a systems programming languages group, we write a lot of papers about the details of the runtime system. So if you're interested in that, you can probably get more information than you ever wanted from the papers. Yeah.